Hello guys and welcome back. It's been a while since the last video, since we finished our BIOS bootloader and handed off execution to our kernel code. And now we are back. We are back with a need for UEFI bootloading. So yes, we are going to embark on a side quest to make a UEFI bootloader before we get to actual kernel stuff. So let's get cracking. First of all, we are going to do a bit of an introduction of what UEFI is and what it lets us do. So UEFI, or Unified Extensible Firmware Interface, is a specification that basically wants to unify how the operating systems talk to the platform firmwares and devices. And it also wants to streamline or unify the OS boot process. So that's what they are saying here in this introduction. And of course, you'll find all the links in the references file on the GitHub. So UEFI is a proper specification, unlike BIOS, which is, for lack of a better term, a sort of vibe, I'd like to say. So people just did whatever they felt like doing. There was some things that were more or less common on all platforms, but once we go out of our way to use something that's advanced, we are going to find quite a bit of quirks and whatnot in BIOS, whereas the U in UEFI stands for unified, so pretty much everyone has to follow at least these specs. So let's go over an overview of what UEFI has to offer. So we have a boot manager, for UEFI, which basically inits the platform, tries to load drivers and applications for the devices that it finds, and then tries to create a list of all the bootable volumes and try to find if there's a bootloader on those volumes. And then it tries to call every bootloader and sees if it fails or not. And then when some bootloader succeeds in loading the OS, it calls this boot services terminate thingy here, and then hands off execution to the operating system. So that's what the boot manager does, more or less. And we can have a few different, types of applications in UEFI. We have applications, which is basically what we are trying to write for now. We have OS loaders, which basically what our bootloader will be once we hand off execution to our operating system, or when we basically get there. And we have drivers, which are the drivers that are loaded by UEFI for certain either components or drivers that offer some services for other applications. And so the firmware core has two sides. Basically, it has the boot services and it has the runtime services. So boot services have these are structured as these protocols. So every protocol is basically one of the many things that we need for booting devices. So we have a protocol to load files, a protocol to read from keyboard, a protocol to write to screen and stuff like that. And the runtime services are services that basically make the OS's life easier. So basically we can, if we want to, we can use them to get the current time, set the current time, set variables, set a virtual address map, convert a pointer from physical to virtual address, and stuff like that. We can reset the system or reboot the system. So we can do quite a few interesting things with runtime services. And the difference between boot services and runtime services is that once the OS takes over, so we hand over control to the OS, and we go through this this thing here where we terminate the boot services. The boot services are no longer available to us, and whereas the runtime services are still available, given that we respect a few things that we are going to see next. So let's go ahead and see calling conventions. So under this calling conventions, we can see the listing of data types that are used in the spec and what they actually mean for a computer. And we have, for every platform, we have calling conventions and sort of the state that the CPU will be in, the minimum guaranteed state that the CPU will be in once your application, your UEFI application gets run. And of course, there's something here that I wanted to go over. Right, so after the operating system calls exit boot services, which basically terminates the boot services, firmware boot services are no longer available, and it is illegal to call any boot service, meaning that police officers will come to your house if you try this. So don't. At least I know I won't. Right, x64 platforms. This is what we are interested in. I guess it's fairly important to mention that UEFI applications and drivers and whatnot are PE32 plus files, PE being the Microsoft Portable Executable File Format. So we are going to need to compile for that file format. And the Microsoft ABI has a specification for UEFI applications or EFI applications. So we'll make use of that to compile this. Otherwise, let's go through these things here. So during boot services time, the processor is in the following execution mode. So uniprocessor, meaning that SMP is not enabled. Long mode, 64-bit mode. This is very good because, well, just remember what we had to go through to go from real mode at the very start to predict mode and then to log mode. So we had to actually go through quite a few things, to say the least. So paging mode is enabled, and any memory space defined by the UEFI memory map is identity mapped. Identity mapped meaning that the it's written here. Every virtual address is basically identical to the underlying physical address. Right, we don't really care about that. Selectors are flat, we don't care about that. Interrupts are enabled, though no interrupt service. Right, so interrupts are enabled, so we might be surprised by that, but there are no services that are using interrupts other than the boot service timers. Okay. And they also say that even the device drivers are not using interrupts, so they are pulled. Direction flag is clear, so other flags are undefined. 128 KB of stack space, it's good. Stack is 16 byte line. That's a bit overkill for x64, but I guess they want to have something unified for all platforms. I know that ARM in ARM64, in ARC64, we need the stack to be 16 byte aligned, whereas in x64, 8 byte lines would suffice generally. Stack may be marked as non-executable, okay. Floating points, multimedia extensions, EMTS, we don't really care about those. So for an operating system to use any UEFI runtime services, so these are the guarantees that the operating system needs to make in order to be able to call into the UEFI runtime services like get time, set variable, get variable, etc. So let's see what those are. There we go. So preserve all memory in the memory map marked as runtime code or runtime data. Call the runtime service functions with the following conditions: long mode, 64-bit mode, paging enabled. So flat selectors and virtual address identity mapped. Direction flag clear, 4 KBs of stack space. 16 bytes aligned stack. So floating point, we don't really care about those. Interrupts may be disabled or enabled. And some things about ACPI, which we don't care about. Handoff state. So handoff state is basically how our application's entry point is getting called. So the convention here is that RCX will have a EFI handle and RDX will have a pointer to an EFI system table struct, and RSP is some return address. Right, detailed calling conventions, we don't really care about those. Right, so that's pretty much everything that we care about in that section here. So protocols. Protocols are basically services that the UEFI system offers us as application writers. So every protocol has a globally unique ID. A protocol has an interface structure, and the protocol services. So basically, these three are the protocol specification. And here they go about how protocols are defined. We're not really interested in that. So this is what I'm interested in. I want the list of protocols. So there are a few that I want to point out. So for example, load file protocol reads a file from an arbitrary device. Simple text input protocol so supports simple console style text input and simple text output. So same thing, so console style text displaying. So, okay, these two will be interesting. Pointer protocol, simple pointer protocol. This is for support for mice and trackballs. So this is reason why in newer UEFI boot screens, we can use mice to click on things instead of the older text-based BIOS boot screens, where we had to navigate using the keyboard. So file protocol, disk I/O, block I/O, PCI, USB, network, graphics output protocol. So interfaces for devices that support graphical output. So this is basically our video modes to be able to get a frame buffer and write pixels to the frame buffer instead of just writing characters, which is what the simple text output does. Okay, and I guess we have quite a few other things here. We have ARP for resolution, network resolutions. We have DHCP, we have TCP, IPv4, UDP. So quite a few things here. I think in the newer versions we also have IPv6. Not seeing it here though. All right, so driver model, we are not writing a driver, so we don't care. Right, boot manager, and I'll go directly straight to this boot mechanisms here. So I'll try to summarize what this says. It says that we have a file path that gets looked at by the BIOS system. This file path here has a prefix of EFI/boot. And then the file that looks for is called boot and the machine type short name .efi. So on x64, it will be boot x64.efi. So if we put a file on our volume or our boot disk in folder EFI/boot/boot, and we call it boot x64 EFI, it should get run on system startup basically. So we get some network booting and stuff like that, which we don't really care about for now. Right, so that's pretty much it for the introduction to UEFI. I'm trying to speed run this because it's the second time I'm recording it. The first time I had forgotten to enable audio recording. So here's what an example application looks like in EFI. So we have this entry point here we called EFI main. Takes a EFI handle H and a EFI system table pointer ST. System table pointer has a, I guess, pointer to a protocol, which is conout, which is a simple text output protocol, and that protocol basically defines a function called output string. that takes a string and outputs it to the display, the screen. And to build this, have a single make file here. So I'm using Clang for pretty much everything because it already comes with all the cross compilation targets that are needed. For example, here we need x64 Windows triplet, x64 unknown Windows triplet, and we need to link against a subsystem or the subsystem EFI application in the Windows API. So that's what we need to do. Right, so I built the .o file from the C file, and then we link it here using the use LLD link by specifying the entry point being EFI main, that's what we called it, and we specify that we want a subsystem EFI application. And then here, in this target here, we just create a bootable disk. So that's how we can make a EFI sample application in C. But we're not using C. We are using, drumroll, we are using Zig for this. The reason why this video has been delayed is that I've taken time to actually use Zig for a bit. So I've been using it on and off for a little bit more than 2 weeks now. Overall, I like the language. It gives me all the control that C gives me with some sort of securities to avoid foot guns. But I also have a bit of a gripe with the language, and I'll show you what I mean. So if I go here and do const x equals 0, unused local constant. So this is an error. This will make compilation fail. And to get around this error here, we need to do something like this. Okay, so now we have no more error. Compilation will go through. The only problem is that if you are trying to solve the problem where you have a lot of unused variables in your code, and you want to set that as an error so that people actually pay attention to that, you don't do this. Because if you do this, now I have variables that are unused, but I have no error. And I have no warning. And I have nothing that tells me that my code is actually littered with these kind of things. To me, they try to solve a problem that wasn't there. And their solution was not even that good. Just make this opt-in. If I want this to be an error, I want to tell you that I want this to be an error. Make this a warning by default. I don't want to have to work around this, and now I have no warning and no errors, and leave my code littered with these things. Especially if I'm iterating on my code. I want to be able to do this, see this as a warning, ignore the warning until I finish my code. And then I go ahead and clean it up. And then if I need to, I can enable that this would be an error so that my release build does not have any unused variables. Anyway, let's take a look at what changes I had to do to make these things build, and then we'll come back to look at the Zig code. So first thing I did was move the first and second stages BIOS bootloaders to a new BIOS folder or subfolder under bootloader. Also adapted the make file to point to the right build directory. I've also created this make file here that basically builds both the BIOS and UEFI bootloaders. And in the build folder here, I have added this this here, which creates the EFI/boot folders, and this here, which basically copies the boot.efi, which is what we are building from Zig, into EFI boot, and then renames it boot x64.efi as we've seen in the specification. So those are the changes that needed to be made for this to compile and run. So let's go back to Zig and see what we did to build this. So first of all, this is we create a custom built target here. So we want x64. We want this OS tag to be UEFI, so that Zig has some internal handling of how UEFI targets are set up. And basically, instead of us making an entry point, a UEFI entry point, as the spec said to do, that takes a EFI handle and a pointer to a system table. Zig handles that for us behind the scenes, and we just need to make a simple Zig program that has a main function in it, and we can get the system table and other handles from Zig. The ABI, we are using MSVC just so that we can get the EFI application targets and stuff like that. Otherwise, we are creating an executable that we are calling boot. And of course, we are compiling our root source file being main.zig. And then we install the executable so that we can have it in zig out/bin. And that's what this main file here does. I do not want to rely on the Zig build system to do everything. So I'm just calling the Zig build to get the boot.efi out in the exe install path, which is zig out/bin by default. And then I copy that manually to our output there, which is the build folder. So that's pretty much what this make file does. I also have a git ignore here just to not push the Zig specific folders. Right, so let's take a look at main.zig. So as with any Zig program, we import std and we import UEFI from std.os.uefi. And we'll see what this is in a bit, but this is just a sort of alias for this function here, std Unicode UTF-8 to UTF-16 string literal. Right, so from this UEFI that we've created, we can actually access the system table and other things UEFI. So if I just go to its definition here, we can see that we have quite a few things that are set up for us. One of which is the system table pointer. So we get that, we get the console out from that system table pointer. It's a nullable pointer, so we need to do a check, but I've opted, since this is just a toy example, I've opted to just get it out of the nullable by doing this dot question mark operator. And once we have console out, we can do a few things. So for example, here I clear the screen and I output a string. And here is where we use this UTF-16 alias that I've created. And what this does is it takes a UTF-8 string literal, or UTF-8 string literal, and converts it to white cars. So Windows style wcar. And it outputs that to the console. And see, to link this to the rent from before, since every single function in UEFI spec returns a status, as we can see here, we need to basically prefix all of them with this thing here to swallow the compile error that will happen if we don't do that. Again, please don't make your language shitty by pushing your opinions on someone else. Just make things easy to use. Make things opt-in. Use sane defaults. Thank you. Right, enough of ranting again. And right, so I'll rant just a bit more. I've been using the language for a bit more than 2 weeks, and I'm getting a bit disheartened by this. Every time I see an error and I need to go and add this at the start of a line, I get so freaking mad just at the clouds and at Andrew, who basically forces his opinions on me. So yeah, I don't know if I'm going to use Zig for the kernel. That was actually the plan. I was planning to use it for this UEFI bootloader as sort of learning the language kind of thing, and then use it for the kernel as a main project, I guess. But yeah, this is just unbearable, really. So enough rant. Right, so here we get the boot services from the system table. Again, this is a nullable pointer. So we just get the pointer out of the nullable by this question mark operator. And we get the console input here. We create an event array that basically has one event, which is console input wait for key. And this event here is called every time we press a key in the console. And what we're doing in this program here is we call boot services.wait for event. We pass it the events array, and we get out an index, which is basically the index of the event that fired. And basically this loops here, this while loop goes on until we get an event that fires. We have the index here. We check that we have the index that we expect. So this one is, we have only one element. So index 0 is the only one we have. So if index is 0, then we go ahead and actually read the key that was entered on the console, because this event here just says, it's sort of like an interrupt. It says, there's something interesting. You might want to go look at it. So we read keystroke, we pass it this input key variable here, which is a key.input struct. And if we do a check here, if the input key, if the Unicode car of that input key is the same as capital Q, we basically exit our program by returning this status code here. Otherwise, we basically just convert that single car into a U16 string literal, and we output that string to console. And then, of course, this one here, I've put a return, but this is technically unreachable since we either exit here or we keep on looping forever. Right. So let's build this and see what we get. One very important thing before we run our project, you will need, for QEMU does not support UEFI by default, it only supports BIOS. You will need a UEFI firmware for QEMU. And that UEFI firmware is OVMF. At least that's what's most widely used. If you're using one of the mainstream, I'd like to call them, Linux distributions, you can just install OVMF by using your package manager. If you're using something that's non-standard, then good luck with that shit. Right, so let's build, that should be all, let's build this. Okay, and we need to specify this BIOS parameter here to UEFI, and we give it the path to so ovmf.fd, which is one of the files that was installed when I installed OVMF on my system. And now we have this running here. Right. Yeah, might want to do this correctly. So x64. Let's run this again. And this time we have our program. So we have our hello there that was printed early on. Console was cleared. We have this hello word there. So now we are going to attempt typing something in and seeing what we get. So hello there. Okay, does backspace work out of the box? It does work out of the box. Okay, does carriage return work out of the box? It does not. Right, so let's try. Okay, it's definitely a bit slow to exit. Okay, just have to type slowly. This using capital Q. So I'm going to hit capital Q and I'm expecting this to exit. And of course it does. And when this exits, we basically land on the OVMF boot manager. And what we can do here, we can do something very interesting. We can actually request the EFI internal shell, which will basically bring us to this screen here. And we can examine the file systems that we have mounted. So by using mount, we are listing the file system. We can see that we have fs0, which is our file system. So if I do this, it should be inside that, and I can ls to see that we have basically the same structure that we created, file structure. So if I go into EFI/boot and ls there, we can see that we have our boot x64 EFI file. And if I run that, I should get my program again, hello there, and we should be able to see this. And if I hit capital Q, we get back to the shell. If we exit the shell, we get back to this boot manager screen. And if we can also choose to boot from a device, we know that we are mapped as this hard disk because we asked it to ask QEMU to mount our image as a hard drive. So if I hit enter here, we should also boot into the bootloader on that hard disk. And again, we have our system working. Well, that was it for today. We went through an introduction to UEFI and seen a example program that basically does some basic stuff. And this project is looking like it's going to be a lot of fun, especially while learning Zig and using UEFI. There's quite a bit I'm going to learn along the way. So hopefully you have fun also watching this and probably following along. I will try to start live streaming on Twitch at least once a week if I can make it. I will not work on OS dev during my live streams because I know that people will not watch that. But I have other more fun projects that we can work on live, and that will be quite a bit more captivating, I guess. So keep an eye out on the community tab of the YouTube channel, or follow me on Twitter so that you don't miss when the live stream schedule gets announced. Well, that's pretty much it for today. I hope to catch you next time. Until then, see ya. Take care.